Oh, hello everyone. This is our follow-up FEA workshop with Rob about contact problems. All right, so take it away, Rob.
Hey, okay. So yeah, the last session went way long on that topic, or on the topics that we discussed then, and weren't able to get into contact problems. So I'm going to pick up more or less where we left off. And let's see, so you should be able to see my screen now. Everyone confirm that?
Yep, we can see it.
Okay. So I got your CAD. So thank you for sending that over, guys.
This is one of the flagship bots. This is Murphy, just for some context.
Okay. Now, is this a 15 or a 30-pound weight class?
This is 15. It's a little bit overweight right now, which is
okay.
Why we want to do some FEA on it to see where we can cut weight from it.
Okay. So I'll be getting into contact as it applies to this model probably in the second hour. I'm going to spend some time now building up kind of the basic concepts on sample models, similar to what I did last time. So I have picked out the a sub-assembly of the weapon model that I'm going to look at when that time comes. So that's going to be this. But in the meantime, let's get into kind of the basics of contact. So SOLIDWORKS offers a number of different options for defining contact between parts, of course. And let's just start right at the beginning. So the way you define contact between two parts, it's under the connections menu on the feature tree of your assembly, or of your model. Once you get into the simulation, you'll find it under connections. There's a header for component contacts and a header for contact sets. Now, component contact allows you to pick entire bodies, entire parts that it will simulate contact between. So I don't have to pick individual faces. I'm just going to say this part is going to touch this part at some point in time. And computer, I want you to figure out where they might touch, and just do all the work for me. And there's a few options. One is going to be no penetration. So that's, kind of more, we'll call it a more realistic form of contact, where parts can pull apart from each other, but they can't overlap with one another. There's bonded, where you're just going to pretend that the two parts are one solid object. And then there's allow penetration. Now, allow penetration is kind of the opposite of bonded contact or no penetration, in the sense that this is an exception to, this only works as an exception when you have an existing global bonded contact rule. So for example, here, this is the default that pops up when you create a new model with multiple bodies in it. It's going to create this thing called global contact bonded. Oops. And it starts off as unsuppressed, and it assumes that all the parts that touch are bonded together. 99% of the time, I don't find that useful, so I almost always end up suppressing it, or just flat out deleting it. But if you left it in, then you could explicitly say that, say, for example, this part and this part are allowed to overlap one another. I honestly never use it as an option, so I'm not going to go into any more detail about it here. So I find that general component contact is not quite as useful to me. So let's go into contact sets. So a contact set, you can just right click here and you can create a contact set. And this, now you're going to be picking individual faces. And we've got, instead of 3 options, we have 5 options. So we have the no penetration, the bonded, and the allow penetration, but now we've got something called a shrink fit, and we've got a virtual wall. Now, I'll get into these two a little bit more later, but no penetration, bonded, and allow penetration are basically the same as what I described before, except now you're picking individual faces. So now I'm going to say that this face and this face are not allowed to penetrate one another. And you can define things like friction, and you can tell the computer that there is a gap between those 2 parts. I'll talk about this more later. Let's set this problem up here. Delete that. Delete that. Gonna edit definition. Okay. Okay. So I've already created this pair of brackets. You might recognize this one from last time. And I've got an upper bracket, I've got a lower bracket, and then I've got a little, we'll call this a washer or a clamped part. You know, this could be something sandwiched between these two. And notice how I have the fixed constraint here, and I'm applying a force here. Let's see. We're going to then create a contact set. And we're going to say that the bottom surface of the top bracket and the, let's see, is that the right one? Yeah. And the top surface of that part are not allowed to penetrate one another. Create another contact set. And we're going to right click, select other. See, that is the clamped part. Oops, didn't take. Select other. Is that right? Clamped part, FEA bottom. Okay. So now I've explicitly declared that these 2 faces are not going to, they can't overlap. And with a force being applied between the top of this bracket here and this bracket down here, if I simulate this, it should show a perfect stress pattern that clamps these two, clamps this part right in between. So let's create our mesh. And I'm just going to use the default settings here. Now, if those of you who are here for the last session may remember, you know, the meshing rules for the fillets, where I say you want 4 elements through the radius. I'm going to ignore those rules for the time being. And we've got a mesh, and we'll just run the study. And it failed. Okay, this doesn't seem like it should fail. Why would it fail? And this is one of the difficulties that you'll run into with contact problems when you're first starting out, is that you still need to consider your part's constraints in all 6 axes of motion. That is to say, you've got motion in the X, Y, and Z translation directions, and you also have rotation along the Z-axis, X-axis, and Y-axis. And in the case of actually both the top part and the part being sandwiched, this part being sandwiched is actually not constrained in any direction. It's got a potential sandwiching, but in the y-axis, but any microscopic imbalance of force in the z-axis or the x-axis will cause it to fly off to infinity because it's not constrained in those directions. One way to get around that could be, for example, to add friction. And we'll just leave the default 0.05 friction coefficient, and we'll set friction on the other part as well, or on the other interface as well. Let's see if that solves it. It's probably going to fail. Oh, I guess not. Okay. So as you can see, when you're simulating contact, particularly between parts that don't have boundary conditions directly applied to them, you still need to make sure that all of those parts are constrained in all of the appropriate axes. And they can fly off to infinity if and cause the model to fail if that's not the case. So let's talk about how the different contact sets are created. I'm going to go to a simpler model here. Okay, so here I have 2 blocks. I've actually modeled them on the same, within the same part. They're part of the same solid. Well, not the same solid, but they're part of the same part file. And we're going to look at how SOLIDWORKS forms the contact between these 2 parts. In this model, I've constrained one end of this block, and I'm pulling on the other end of this block. Now, if I have contact, whether or not I have contact between these 2 parts, you would think that this block off on the right would fly off to infinity under a pulling load. And as you will see, that is not necessarily the case. I'm going to delete that. Yeah. So let's start with bonded contact. When SOLIDWORKS creates bonded contact, what it's doing, well, let's mesh this part first, just to show. Okay, so you can see that this part is meshed with a bunch of different tetrahedral elements, and on the surface they look like triangles. And we have a different number of tetrahedral elements on this side as we do on this side. And obviously the surfaces are not touching. I've modeled them with a gap. And so if I wanted to, say, for example, create a contact between these 2, SOLIDWORKS is not smart enough to tell me that these 2 parts are not touching when I tell it that there's contact. So let's make a contact. Contact set. We're going to declare bonded contact. Bonded contact between that surface and that surface. And we got to remesh. Every time you change contact, it'll force you to remesh. Now, what you can't see is that under the hood here, as it were, SOLIDWORKS has said, okay, these 2 surfaces are bonded together what it's going to do is it's going to create virtual, we'll call it lines or straight line elements between every vertex of each of these triangles. So there's basically a little tiny spring between here, and a little tiny spring between this vertex here, and this vertex here, and this vertex, and this vertex. Basically, all it's doing is it's looking at each vertex, and it's finding the nearest 2 or 3 or however many other vertexes on the opposing face there are, and it's creating a little invisible spring between those two elements or those two nodes. And it doesn't matter if the two surfaces are actually touching. So you would think that if I put a tension on these parts, that the part on the right would fly off to infinity, but that is not the case. As you can see, it solves very readily. And in fact, you can see, well, let's just do this. Let's edit the sketch to show the appearance a little bit more readily. Let's call it 1 inch. Okay. So you can see that there's a stress pattern on the face of the larger part that directly kind of is coincident with the footprint of the part that it's theoretically bonded to. And this is important because what's going on under the hood, where it's forming these individual elements, these little tiny springs between the two faces, that is just as computationally efficient as simulating a single solid part. As long as all of the parts in your entire contact model are bonded together, it will simulate just as fast as a single part. There's no computational penalty for it. But you can also get some inaccuracies. Case in point, these parts are not touching, and yet it's telling you that this part is physically capable of pulling on this part. It's not really realistic. So now what happens, what's going on if you do penetration? So I'm going to change this. And I'm going to say no penetration. Okay. Create mesh. Okay. Now we've got a pulling force on this block, and it's pulling away. Now what's happened? Now when you declare a no penetration contact, this is where the computer starts having to think. And what it's going to do is it's actually going to form little triangles, not tetrahedrons, but little triangles that line up with each face of the tetrahedron. So this is a tetrahedron right here, and it's going to take this triangle, which represents one face of the tetrahedron, and it's going to put an invisible two-dimensional triangular element on there, infinitely thin. And that triangular element is basically a target. And what I mean by that is the computer is going to apply the load to whatever faces have a load applied to them. And it's going to then check to see whether a normal force exists between this invisible triangle and any other invisible triangle on the opposite face that you declared as the source for that contact. So in this, for example, edit definition, your first picked face is going to be your source face, and your second picked face is going to be your target face. And so it's going to check, okay, every triangle on the source face, are you near a target face? If you are, okay. Is there, are you trying to move into one another? Yes, okay. I'm going to put a little tiny spring between you. Okay, now I'm going to rerun the model with that spring in place. at all the elements where I thought that there was contact. And then, okay, now how many of those springs have tension on them? Well, if the spring has tension on it, that means the parts are being pulled away. So I can't actually have the spring element there. So I need to reiterate. And basically, it's going to solve this model 5, 10, 15, 20, 30, a million times, basically turning on and off the individual springs between these two faces until all of the springs have compression and none of them have tension. There's a significant computational penalty associated with no penetration contacts as a result. And you can run into situations like this. Solver failed. Why did the solver fail? Well, let's see. It's going to keep going. Yeah. Okay. Let's look at my displacement. My displacement here is 537 millimeters. So something's wrong, obviously. It's, this part on the right wants to fly off to infinity. And in fact, I'm lucky that the model even solved it all. Usually it just says error. But I think you get the idea. So let's change the direction of the force. Let's cause the force to push the two blocks together. Now the force is pushing the two blocks together. And they have a gap between them, of course. I'm just going to check to make sure that, okay, so that's all the defaults there. Run this study. Initial solver failed. And it's going to run and run. Okay. Oh, we got lucky here. Okay. So it actually was able to detect that the part on the right touched the part on the left and then stopped. As you recall, the displacement going the other direction was like 500 millimeters. In this direction, it's 2.54. That is exactly the gap between the two parts. But what will often happen is you can declare a contact between two parts that have a gap here. Like that, you can declare contact between these two faces and then simulate a force on them. And if the computer may not understand that they touch, or it may miss the fact that they touch, and this part can actually fly off to infinity going into the left. It will actually completely fly through the other part. That didn't happen here. Sometimes it does. So as a general rule, when you use no penetration contact, you want to have the parts already touching. If they are not touching, here, I wonder if I can make it. No, let's see. If they are not touching, you want to use this feature here called gap. And this basically tells the computer there is a gap between these two parts. I want you, computer, to take those invisible triangles that are on each of the faces of these parts, and I want you to offset those invisible triangles by a certain amount. Basically, it'll figure it out for you, but I want you to offset those triangles by a certain amount so that they do touch. So what will happen here is all those invisible triangles, this part has a 1/10 of an inch gap. Those invisible triangles are going to offset from the surface by about half that distance so that they start touching. I'll just verify that here. Always ignore, I'm gonna make sure I've got this right here. Always ignore clearance. Yeah, I think that's right. Now notice how it didn't give me any errors about excessive displacements. That's because when I solved it with the gap option disabled, it was actually able to make this part here move. Here, I'm going to change this. Make this UZ. Okay. If you recall, when there actually was a gap, but I had the gap option disabled, the part on the right actually did move the entire distance of the gap until it touched. When I have the gap option enabled, it's basically telling the computer, you know, offset those virtual triangles, those triangle sensing elements, we'll call them, until they touch. But if it does that, then it's basically telling the computer that the parts are starting off in a touching condition. And as you can see here, my displacement, if I probe that, it's telling me that this part has a displacement of 6.7 times 10 to the minus 7th millimeters. It's basically saying that this part didn't displace at all. So essentially the gap checkbox within the contact set is creating a virtual or an imaginary rubber block, or an imaginary, actually not even rubber, an imaginary block between the two parts that enables them to act as though they're touching even when they're not. So if you're actually trying to see whether a part will deflect or how much it will deflect, it's not necessarily the right option. Now, let's go back into my resultant displacement here. Now you can see that the part of the right, the smaller block, looks like it twisted. It looks like it, you know, kind of rotated off into a weird direction. Why is that? Well, it's the same reason that I said earlier. Basically, these parts are not constrained in any direction other than the Z direction. The part on the left is constrained in X, Y, and Z, and you can see that. It's got an arrow going in the Y direction, it's got an arrow going in the Z direction, it's got an arrow going in the X direction. So this part is as constrained as it needs to be. The part on the right has a force going in the Z direction, but with no friction enabled on the contact, there's nothing preventing it from flying off to infinity in X or Y. And so you get this funky result where it appears to be twisting. And once again, we can rectify that by just adding a little friction. And the block stays nicely aligned. So I'm going to move back to bonded contact. Well, actually, before I do that, so I want to reemphasize that no penetration contact is very computationally intensive. It will take a long time to solve contact models using no penetration. And relatively speaking, the time that it takes to solve a model with no penetration contact is going to be proportional to, I want to say like the square of the number of elements on the faces. So when you simulate no penetration contact, generally speaking, you want to limit the number of elements that are actually declared for contact. So in this case, with no penetration here and here, I've got all of this surface over here and all the surface over here that I know are really not involved in touching. But here, let me just do this real quick. So oops, cancel. We apply mesh control. We're going to pick this surface, and we're going to make those elements super fine. Create mesh. Okay, so the rest of the model is more or less unchanged, but now the elements that are selected for contact are very, very fine. And notice how it's taking, you know, a little bit longer. I apologize. I should have written down how long it took to solve the first time. So it does take longer. And maybe you get a little bit more accurate results, you know, where the contact patch is a little bit cleaner sometimes. So let's do this, create mesh. Oops. Let's delete that. Mesh and run. So you can see that the edges there are a little bit nicer and crisper. So that last one took, I think, about what, like 30 to 40 seconds. So this one solves in about half the time. But of course, the edges are not as well defined. You get these weird kind of effects where it's showing this blended stress area that's not really a blended stress area. So there is some balance to be worked out where you need adequate refinement in your mesh to get a good picture of what's going on, but you don't want it to be too refined. So if I was to add faces, let's say I just select all the faces on that body and all the faces on this body because I'm lazy and I just want the computer to give me the answer and I don't want to figure out what has to solve. So what actually happens? Does it solve any faster? And you can see that it does indeed appear to be taking a fair amount longer to solve because every element, it now has to look for every element on every face that I picked and say, okay, is this element over here touching this element over here? No. So, and now I get really weird results because I declared the gap feature, because I had this gap checkbox enabled, it's now assuming that an element, say for example here, can touch an element over here because that gap checkbox is enabled. So it gives really weird results. So you always want to make sure that you only choose faces that are actually touching when you simulate your contact. It'll solve faster and you're less likely to get odd results. So I'm going to go back to bonded contact. Delete. Yes. Okay. And we're going to look at something called a conformal mesh or a congruent mesh or a matching mesh. Sometimes it's called, I think SOLIDWORKS calls it conformal. So I'm going to get rid of the gap between these two parts. Edit feature. And just delete that offset. So now I've got these two solid bodies and they touch perfectly. And actually, for the sake of the model, this is going to be a little bit easier. So I've got two solid blocks here. And we're going to go back to our bonded contact, which I said was more computationally efficient. And we're going to create a contact set. And we're going to create bonded contact. Oops. Bonded contact between one surface and the other. So let's see, I want that face from Boss Extrude 2, and I want that face from Boss Extrude 1. And let's create the mesh. Okay, now look at what we have here. Because the faces were that are being selected for bonded contact are perfectly matching. They're line to line. They, in other words, the square face from the right block and the square face from the left block occupy the exact same footprint in space. They have the exact same outline. The outline is formed by different curves because one set of curves belongs to the right face and one set of curves belongs to the left face, but they trace over each other perfectly. And as a result, SOLIDWORKS is able to create what's called a conformal mesh. What it does is, remember how I talked about SOLIDWORKS forming, invisible springs between the two faces? Well, when you have a conformal face, SOLIDWORKS doesn't have to do that. It's actually literally welding the two faces together. It's forming them. It's forming all of their elements as part of matching nodes. So, for example, this node here is shared by both the left and the right parts. It's not two overlapping nodes that just have an infinitely short spring between them. It's literally the same node. And this is even more computationally efficient. And I may have been wrong. Okay, so you know how I can know I was wrong, and I just got lucky, is that when you do a displacement plot, you can actually see that one part was able to move and overlap the other one slightly. So that's how I know that what I just said actually didn't occur. So what happened is that it looked like they were conformal, but they weren't. And that's one of the hazards that you can get into, where the two faces appear to overlap perfectly. And if you have two faces that occupy the same space, of course, SOLIDWORKS is going to mesh them the same way. So I should have known, because the option to select a conformal mesh or a matching mesh isn't in the contact sets option. For that, you actually have to do component contact, where you select the two bodies that I said I don't really have much use for. But in this case, we're going to pick both of these bodies, and it's called compatible mesh, sorry. So when you select compatible mesh, okay, delete that. When you select compatible mesh, now these nodes should be shared between the two solids. And when you run the solution and it shows you the outline of the part, theoretically, any parts that are meshed with compatible faces you won't see a line where the two parts meet because it's literally simulating them as part of the same exact solid. And we can verify that. So if I go into my mesh and I can right click on my mesh, I'm going to create what's called a mesh quality plot. And we'll just display the mesh. And then we'll right click on, and this is kind of a workaround. SOLIDWORKS added this as a way to view cross sections of your mesh. So you create the mesh quality plot, and then you right click and you select mesh sectioning. And I'm going to pick not the front plane, but I want the, let's pick the top plane. Okay. And you can see that now it's showing me all of the tetrahedral elements that intersect this plane here. And if you look at the boundary where the two parts meet, you can see this node is shared, this node is shared, this node is shared. All these nodes along the boundary are shared. This is showing one tetrahedral element on one side of the joint, but not on the other. I think that's just a graphical, a graphical bug where it chooses to not display the tetrahedral element on the other side because it's not fully overlapping the section plane. But you get the idea. So if I was to go in, let's see, let's suppress that. And let's just let's show you what a non-compatible mesh looks like. Apply mesh control. So I'm going to apply a mesh control to, oh crap. Sorry, I got to hide this. Okay. Okay, let's go to apply mesh control. And I'm going to select one of the faces, not both of them. And we'll just give it a nice fine mesh. Create mesh. Okay, now I gave the face on one side a fine mesh and the face on the other side not a fine mesh, just a regular old mesh. And you can see that the nodes and elements are not shared between the two faces anymore. And I suppressed my bonded contact, so it's this is just for the sake of viewing it. So if I go back to my mesh quality plot and I view the mesh, you can see that when you section the mesh, it's very obvious that they don't share nodes between the two sides. So if I go back to my bonded contact, I unsuppress that. This is component contact bonded, not picking individual faces. So let's see what happens when I have a forced mesh control on one face, but not on the other, but I'm still telling it to do a compatible mesh. What happens? It will force, it will basically mesh the two surfaces, and it will force them to be treated as one surface. And so even though you applied the mesh quality constraint to one side, it'll get pulled over to the other. And you can verify that by creating a mesh quality plot and then sectioning it. And now you can see that all of these nodes and elements are nicely stitched together. So this, as I said before, is the most efficient way to simulate contact between two parts that are actually bonded because it treats them all as the same solid. So, so if I go back and if I edit this sketch and I make one side different. See, now with the compatible mesh option selected, what it does is it traces the outline of the smaller face onto the larger face. And it, again, forces them to share nodes and elements across that boundary. And so this is useful where you are creating where you're creating trying to simulate a part that you want to behave as a single solid part. So I'll get into that. Actually, let's open another one. FDM. So I had a simulation of an FDM part. Shell-based, solid-based. Okay. So here's a situation where you want to use bonded contact. This is a part that is 3D printed. How do I simulate the fact that it is 3D printed? Well, when you 3D print a part, unless you choose 100% infill, it's going to have different density on the inside versus the outside. So if I unsuppress all that, unsuppress, unsuppress, you actually end up having a multi-body part where you have two solid bodies. You have an outer shell, which is your outer printed layers, and then you have your inner body, which is all of your infill. And this is not technically solid, it's made up of like lines and stuff. But you can simulate different material properties for your infill compared to the outfill or the outer layers by declaring global bonded contact between the inner and the outer bodies. And when you create the mesh, oops, sorry, let's see, sectioning, need to choose a different face. You can see that it meshes very cleanly, where the whole thing is treated as one solid object, and you don't incur any of the contact penalties that you do with, say, for example, no penetration. So I did have an example file of this that I sent to Jacob. I don't know if he has shared it with the rest of the team, but you know, this is, you know, a side project on how to simulate 3D printed parts that he may be able to kind of share with the rest of you guys. And this is a good example of where you would use bonded contact. Looks like we're hitting the 1 hour mark. So if anyone wants to take a break, I'm game, and we can come back in 10 minutes.
Yeah, let's do that. I'll pause the recording and we'll be back in 10 minutes.
Okay. All right. Let's continue. You can record whenever you like.
Yep, we're going.
Okay. So just to be absolutely sure, so does anyone have any questions at all about the contact problems that have been done so far?
Maybe you could just give us a quick summary of when it is appropriate to use bonding contact and when it's appropriate to use shoot, I forgot the name of it. the one where they're not intersecting contact.
No penetration?
No penetration, yeah.
Yeah. I can't give you a general rule, but I can say that, you use bonded when you want the parts to behave as a solid object together. You use, and when you expect them to behave as a solid object together. And when you expect or don't care that they can transmit forces in all directions. So that includes shear, pressure or compression, tension, twisting, basically all of the things associated with the moving to solid object is when you can safely use bonded contact. If you were welding two parts together, for example, you could use bonded contact. Now, you would need to make sure that they were only bonded along an edge where the actual weld bead is, but that's neither here nor there. You can use no penetration in cases where you need more realistic results, and you can combine no penetration with forces that keep the two parts mated together, and deal with the associated computational slowdowns if you have to. So actually, the example I'm going to talk about here is going to get into why you would choose bonded versus no pen. I'm going to get into the keyway, for example, right here. So we're going to look at the forces that get applied to this weapon disc when it hits something and how that transmits into forces on the keyway. So let's get into it. So I've created this basic model here, and I'm going to kind of start with a little bit further back than contact. So we're going to go back to the issue of an unconstrained model. So in this weapon shaft assembly, we have not a fixed constraint on the ends of the shaft, but in fact, I've created bearings. So I'll just delete that here. Yeah. And the way you do that is you go to fixtures, you right click, and I'm going to select a bearing fixture. And I'm going to select a cylindrical face. And it's going to basically take that face, and it's going to find a point that is the centroid of that face. And it's going to put a bunch of little miniature springs, just invisible springs, same as with bonded contact, really. It's going to create a bunch of invisible springs from every node on that surface down to the center of the surface, which is in here since it's a round surface. And then it's going to apply constraints in one of the 6 directions, X, Y, Z, rotation X, rotation Y, rotation Z, to that point. And the default is that it's going to allow rotation in the Z axis, and it's going to prevent rotation in the X it's going to also allow rotation in the X and Y axis with this checkbox that says allow self-alignment. But it will not allow translation in the Z direction, nor will it allow translation in the X or Y direction. So if I uncheck allow self-alignment, now it will only allow translation or rotation in the Z axis. It will not allow rotation in the X or Y. This can be handy sometimes, where if you want the part to pivot, like say this was a ball, a swivel ball, you could allow self-alignment and it would behave properly like a swivel ball, but I'm getting into way more detail than I need to here. So I'll just use the pin to keep this menu open, hit OK, select this other face, create a new one, hit OK, cancel out. And because I created them all in the same operation, I now have a bearing group. Now, these parts, or these 2 bearing constraints, do not allow the part to rotate they do allow the part to rotate in the Z axis. So if I apply a force, say 100 Newton force, to the tip of this weapon disc, what's going to happen? Well, it's going to spin off to infinity. Oops. Sorry, with the default settings, it is just going to spin off to infinity. Solver failed. Model unstable. Okay, so it wasn't able to solve. I'm going to enable an option here in the right-click properties, and I'm going to enable this option called Inertial Relief. And it's basically going to say that anytime there's a force imbalance in the model, we're going to allow the part to undergo rigid body acceleration, and so it's going to apply inertial loads, basically like, you know, G loading, to the entire assembly to account for the force imbalance. This is something called de Lembert's principle. See if I can Google it. Okay, this is called de Lembert's principle. Basically, you would use this to simulate, for example, a rocket. If you were on the hybrid rocket student group, you would put a force at the back end of the rocket, you know, pushing it upwards into the sky. But obviously, there's nothing holding it down except its own inertia, and so you would use inertial relief to account for that. So if I have the inertial relief checkbox enabled, so properties, inertial relief is now checked. Hit OK. Everything is bonded in the study. There's a significant external imbalanced force, which will be balanced by the application of opposing inertia forces. Unless you're OK, so yes, that is what I checked. I told it to do that. Okay, and this is the stress pattern. And if you look at the displacement pattern, you can see that there is some radial displacement out here and some strain. Now, for whatever reason, I haven't figured out how to get it to tell me what rigid body motion it's actually undergoing, but basically it's a centrifugal or it's a rotational acceleration, which is pretty obvious. But because I selected bonded contact, you see, hey, there's no line representing the boundary between the keyway and the weapon disc. And the only reason there's a line between the shaft and the keyway is because, well, there's a 90-degree angle there. But as this model is currently being simulated, the shaft, keyway, and disc are all part of the same solid. And guess what? We're not seeing really any stress in the keyway. Yeah, there's plenty of stress over here, but there's no stress in the keyway. Now, that doesn't make a whole lot of sense. You know, that keyway is seeing some load because all of the force that goes into the tip of that tooth is going to cause the disc to accelerate, but it also has to cause the shaft to accelerate rotationally as well. So you would expect to see some shear loading there. So this is a case where bonded contact is wrong. Realistically, with the sharp corner that's in the keyway, you'd expect to see a nice stress riser, almost like a crack, occurring somewhere in the vicinity of the keyway on the disc side. So if I go over here, I've created this other model. And I've created no penetration between all the different surfaces that represent the shaft and the disc and the keyway. And I'll just delete that so I'll get some experience creating it from scratch. So I've suppressed the global bonded contact. right click on connections, create a new contact set. And notice how all these parts are like line to line, they're facing one another. And picking all the different opposing faces is just a pain in the ass. So, I got to right click, select other, scroll down the menu and make sure that I pick the correct face. I don't want to bother with that. So I'm going to use a tool called Automatically Find Contact Sets. And this is going to look for touching faces between two parts. And I'm going to say between this part and this part, find all the faces that touch, find contact sets. And it's going to get me a list of all the faces that touch. And it's going to say this face highlighted in blue. It's really hard to see, but there's a blue outline and a purple outline. The blue outline is the smaller face of the inside of the weapon disc, and the purple face is the side of the keyway. And it's going to allow me to create that as a single contact set. And it says no penetration. Just pick no penetration. And then as soon as I click this button here, it's going to take the one that I have selected. This is the tentative contact set. As soon as I click this button, it's going to move those two faces and create into a new contact set. And this is really convenient because notice how it's only creating a contact pair between faces that are actually touching. So for example, if I picked all the external faces of the keyway and all the internal faces of the weapon disc, that would be a little bit wasteful because forces on this side of the weapon disc don't touch faces on this side of the keyway. So it would be wasting computational effort to try and determine when it actually goes to simulate, oh, is this touching this? No, it's not. So using the automatic contact finding tool, I can just say, oh, that's a contact set, that's a contact set, and this top surface, that's a contact set. And it's all creating with no penetration. And then I'll clear selections and I'll pick the keyway and the shaft, and I'll find contact sets there. And it found a contact set between the left side of the keyway and the shaft. And I'm using no penetration, so make that, make that, make that. And then one more, I'm going to select the shaft and the weapon disc. And it only found one contact set, and that is the, the circular interface between the two. Go. And the net result is that I get 1, 2, 3, 4, 7 new contact sets, and they're all highlighted as no penetration, and they're all clean and easy to work with. I'm going to delete them and I'll create it again, but this time I'll select all 3 parts. So bing, 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 all 3 parts, and now it's going to look, instead of having to select 2 individual parts, I just say all the parts, find contact sets. Now it finds all 7 contact sets all at once, and I'll just do a click and then a shift click, no penetration, create contact sets, and they're all done. So I've got 7 contact sets, same as before, and they're all selected for no penetration. And because they're all line to line, I don't have to worry about whether that gap option is enabled or not. So I'm going to make sure that I have inertial relief enabled. Properties, inertial relief is enabled. Okay, and I've got material properties for all my parts. Just pick carbon steel. And it's going to mesh. And it's warning me that it's taking advantage of inertial relief. And notice how much longer it takes to solve. You know, that bonded contact just solved lickety split, bing, bang. here, now it actually has to think, okay, which elements are touching which other elements? Okay, are they pulling apart from each other? If they are, then I have to remove that contact. But it'll get there. Okay. And now you can see there's actually a border between these two parts. If I zoom in here, you can see there's a black line, and that represents the boundary between the two parts. And I actually have a little bit of a stress pattern there. Now, if I look at my mesh, you can see I'm not following my meshing rules at all. You know, remembering 4 elements through the thick 4 elements around a 90-degree arc. There is no arc. This is a sharp corner. So if I refine this mesh, the further I refine it, the worse and worse the stresses are going to get. But one of the other things that's preventing me from seeing a stress on the keyway is the fact that the inertia mass of or I should say the rotational inertia of the shaft is actually not very high. So the motor, or sorry, the disc is undergoing a rotational acceleration, and it's transmitting that acceleration to the shaft. But I'm missing the pulley and the motor, which are actually resisting the impact imposed by the other the enemy robot. So if I want to, say, for example, incorporate that, let's unsuppress the pulley. So I've got the pulley in here. That pulley is pretty detailed. I don't need all those teeth in there. So actually, I'm going to get into this pulley shaft. And if I tried to model this and get all these fillets in here that, you know, make for a really, really detailed, complicated model. So I'm going to create a dummy version of it. So I've already done this. I've created an outline, and I'm going to unsuppress that. And then let's do a, let's see. Well, we'll just leave the 2 bodies overlapping. But I've created a second body, edit feature. It's a revolve. And then I've unchecked the merge result checkbox. And that creates it as a separate solid object within the same part. So we'll just save that. Go back to the weapon shaft assembly. And we'll go into our static simulation. And now, if I look, now I've got this pulley, and that's coming in as another part. I'll click and I'll expand it. And there is 2 solid bodies underneath it. And I'm going to choose the one that's more detailed, and I'm going to say exclude that from the analysis. So just ignore that. And now I have to add contact between the pulley and the shaft. And this is an example of where I would use a bonded contact, because in this case, I care about the stresses being transmitted between the keyway on the weapon disc. And yeah, there's a keyway between the pulley and the shaft, but I'm not really that interested for the sake of this particular problem. So let's just do a bonded contact and forget about the details between the pulley and the weapon mode and the shaft. So contact set, automatically find contacts between here and here. Find contact sets. It found 1 contact set. Click, select bonded, create, done. Okay. And then for the material of the pulley, right click, apply, edit material. And I've chosen zinc here. I'm assuming that this is a die cast zinc pulley. It may not be, you know. And then I'm going to apply a counter torque that represents the torque of the motor being put into that pulley. So let's do external loads. Let's do a torque. let's put a torque on that face. And does anyone know what the torque that motor can output is?
I think it's 5.57 Newton meters at stall.
Okay, and what's your gear ratio?
2 to 1.
Okay, so we're looking at basically 11 Newton meters, say?
Yeah.
Okay. In reality, so just to oops, select a reference axis. Oops. Okay, there's your reference axis. Okay, so we have the motor, which is pulling the weapon in this direction, and we've got a force being applied by the other robot here. In reality, the torque that you're going to see on that is actually going to be a lot higher because you're fighting you're actually transmitting a shock wave of motion down the pulley. But we'll just use this as an example. So because we have inertial relief, the torque caused by this force and the torque caused by this torque don't necessarily have to be balanced. The difference will be taken up by the acceleration that the part experiences, and SOLIDWORKS will figure out what that will be. And it's just going to solve here. And you can see that, as the bigger and more complicated the model gets, because I'm using no penetration contact, it actually takes orders of magnitude longer. If this was all bonded contact, it would still solve very quickly. Okay. So why is the whole part blue, huh? Well, where's my max stress? Dun, da, da, da. As it turns out, when you apply a load at the tip of the disc, and you transmit that load from the disc all the way back to the weapon motor, guess where it goes through? It goes through the keyway. So let me hide, let's see. If I go up here, okay, I'm gonna hide the pulley, click on that, and then I'll go back. So the trick to hide parts, there's a trick to hiding parts when you look at models. One way to do it is to do edit definition on your results, and you can do advanced options. Oh, come on. Why is it not? Okay, this is annoying as hell. You can do edit definition, advanced options, and then you can pick show plot only on selected entities, and then you can pick solid objects, and you can pick which solid objects you want to show the results on. I will just go up into the model tree up here. Sometimes it's hidden, like you have to, drag this divider down, and I'll just show and hide parts. And then you get it to update by tabbing out and in of your model and then going back to your stress plot. It's a little roundabout, but has its advantages. But you can see that now, the stresses in this fillet didn't change. The stresses in this fillet should theoretically be pretty similar to what they were in the last model, but it's showing as blue because now the stresses in the area around the keyway are so much higher that that's what gets the red. Oh, come on. So if I do a section, let's see, results, section clipping, and we'll section through the part. Okay. So you can see that there is stress in here, but it's showing a max of, let's see, I'll cancel the section clip. Cancel that. It's showing a max. Why is it showing such a high max? Why is the rest of the part not showing much red? And that's because we're running into a mesh singularity problem. Because all of this is sharp angles, you're going to have a single point that shows a high stress. So let's try this. Let's do iso clipping. There we go. So if I do iso clipping will create kind of a cloud of that represents where the stresses are in the model. So you can drag the slider and it'll show you the surface where all the stress is. For example, here, that looks to be about 5 megapascals. And you can see it's got these shark teeth, if you will, these individual points of high stress. And those individual points of high stress are caused by basically the no penetration contact not being applied evenly between dissimilar triangles. So there's a triangle that's really small on one side and a triangle that's really big on the other mating part, and it's trying to apply all the force from one triangle onto the other one, and you get areas of very high stress concentration at the boundaries. So this is one of the things you have to worry about when you do no penetration contact. You'll get effects like this. And one way that is often used to, kind of get over that or to kind of bypass that, you can either refine the mesh or you can average out the stresses. And the way to do that is you can right click on your stress result. You can click on list selected. And then you can say, I want the stress on a selected entity. And you could say select other, and I say I want the stress on this face, hit update, and then you can look at, say, for example, the average stress rather than the max stress. You can see that there's an order of magnitude difference between the two. Average stress is 21 megapascals, no, 2 megapascals. The max stress is 21 megapascals. And that max stress is 10 times higher because it's all focused onto a single node. That's an error associated with the contact. So you average it out basically. You can pick a line to average it across. you know, or a face. You may have to do a split face and then rerun the model so that you can pick the face, that split face. But what are we also not getting? We're not getting that stress pattern that looks like a crack coming out of here. And that's because this is a sharp angle. So if I go in here, let me open this part, features, fillet, and we're going to fillet this corner and this corner, and we're going to give them fillets that are more representative of our real part. So this is a 5/1000 inch fillet. And then I'm going to fillet this and this to see if I can hopefully get rid of that fine shark tooth pattern that I just showed. And then we'll go to the keyway and we'll fillet all 4 edges to give them something that's more representative of reality. And I'm going to give them a 10/1000 fillet so that they don't intersect with the faces on the weapon shaft. Now, when I do this, I can go back to my finite element model. And all my contacts actually stay the same. It's still simulating contact between all of the faces here. So for example, so I've still got contact between this face and this face, you know, here and here, and here and here. And I'm just telling the computer, don't bother trying to calculate contact between this, you know, this male fillet and this female fillet. You may have to go back and redo that sometimes, but in this case, we won't. Okay. And it creates a little bit messier mesh. And just so that I can stay consistent, let's apply some rules. Let's apply a mesh control, and let's actually give this realistic sizing on those elements there. Let's put, so that's a 5/1000 radius fillet. Okay, so let's see, radius is 0.005. Let's see, so the chord length is going to be that times pi times 2 for the entire circle, and then divide by 4 to get the 90-degree arc. And then 4 elements through that. It'll be 4. So element size is going to be. So I need an element size of a little bit less than 0.02 of an inch. I'm going to set. Oh, and this is an element. Okay, so if I say inches, 0.0019. Okay. Create mesh. Now this is going to take a little while. But I do get this nice fine mesh. Now, that mesh goes all the way through the part, and there are a lot of elements in there. So I'm going to go to my mesh section, my mesh quality plot. So mesh, create mesh quality plot, display the mesh, right click, mesh sectioning, And I'll set that by 10. Does that get me where I want? Let's see. 15, does that, okay. So you can see that the the fineness of the mesh carried through the entire thickness of the part. If this got too fine, what I may end up doing is create the mesh rule only on the edge here, this little arc, and we can have a coarse mesh through the rest of the fillet, because I'm reasonably sure that the stresses are only going to be on this edge, or that they're going to show up mostly on this edge. But we'll simulate this. And remember, the pulley is still being simulated. It's just hidden. Say yes, can use inertial relief. So you can see that every time I get more refined in this model, it takes even longer and longer to solve. I really want to drive home the point that when you simulate with contact, anything other than straight bonded contact, you really pay for it with your elements. This model has 217,000 nodes, and it's taking 2 minutes longer, two plus minutes. It'll probably take 5 minutes to solve. If you try and simulate a problem and it runs for an hour and then fails, that's something that's really going to piss you off as a designer. And if you keep butting your head against the wall trying to keep that really high mesh density, no penetration contact in there, it's going to keep happening. When you simulate with regular old bonded contact, particularly with compatible mesh, you can have numbers of nodes that go up into the millions, 2 million, 3 million, and it'll still solve in seconds. But as soon as you put in no penetration, your solve times just go to shit. So. And again, what's happening is because there are more elements along this surface here, it has to compare more elements to more other elements. So, whereas when there was only, say, 6 triangles on the face of the keyway and 6 or 7 or 8 triangles on the opposite side of the weapon disc, that's only 48 combinations that it's got to consider. Is number 1 touching number 2? Is number 2 touching number 3? When you've got say 100 elements touching 100 other elements, that's 10,000 possible combinations that it's then got to iterate through. So you can see that, you know, solving the model 10,000 times in a row while it tries to figure out which elements are actually being pushed into which other ones gets very complicated very quickly. Okay. So 5 minutes, I was about right. Okay. And it's showing my max, now it's showing the whole model is blue, and my max stress is 83 megapascals. So if I do my ISO clipping, what's going on here? Ah, see, all that high stress is happening along that thin line. And then if I drop that, let's see what happens if I zoom out here. So that's looking less and less like a singularity and more, you know, whereas, you know, we don't have that shark tooth effect anymore because it's occurring, you know, pretty much uniformly along the entire line. What you're seeing is crack tip stress amplification, which you've probably learned about in some of your early solid mechanics courses, where when you've got a very sharp corner, you have very high stresses as a result when you put a load on that corner. So the entire model looks blue except for this, and this could be the source or the start of a crack in the weapon disc when it hits something. Now, is this number realistic? Are you actually going to see 83 megapascals of stress in that corner? Well, that number is a function of the load that you put into it. So for example, I could change that number by changing the torque that I apply to the motor. I could change the impact force. So for example, if you don't have a good feel for what the impact force is, you could put in the wrong number and get a wildly, you know, different result for the stress in this keyway. But you can see now we've got a pretty good picture of where the stress or of where the peak stress in this model actually is. And because it's not, it's pretty apparent that it's not a mesh singularity. This would be an area that I focus on as the focus of a design change to reduce this as a risky area. You know, you hit something and then you get a crack that cracks, say, starts here and cracks all the way through, say, over to here. You know, removing that keyway or finding a way to attach the weapon disc to the shaft without the use of a keyway would be something that I would look into as a result of this analysis. So, any questions? No questions.
I guess not. Do you actually think that in this application, it's worth looking at replacing the key with something else, or is it like it's hard to tell? Like we have a number, right? Whatever you said, 83 megapascals, which is probably going to be more than what the steel can handle. Would it be better?
Well, so sorry to cut you off. 83 megapascals is nothing compared to what steel can handle, but
okay.
yeah, I mean, if you're looking at making this out of a, say, for example, S7, if this disc is going to be made from S7, your failure strength on S7 is going to be like 1,000 or even 1,200 megapascals.
Oh.
So it's
no,
way higher.
It's right. What we can get from this is not an actual number for how much stress is going to be there, but the idea of where the maximum stress is going to occur, which it seems like no matter how much force you put on there is going to occur at that keyway.
Exactly. Yes.
So if we wanted to make this, if we thought this was going to be an issue and wanted to make this stronger, the way to do that is evidently to get rid of the keyway and replace it with something else.
Yes.
But whether that will actually be an issue or not, kind of remains to be seen. I think it's probably okay, but that does tell us where the point of failure probably will be.
So, this is where you have to couple knowledge of FEA with experience in the field.
Yeah.
FEA will never tell you everything that you need to know up front from the beginning, because it's always predicated on what you put into it. In this example, I have given 100 newtons of force on the tooth. The force on the tooth is going to be orders of magnitude higher when you impact something.
Yeah, of course.
It's going to be, probably, it could be upwards of 6,000 newtons or something, or even more. And the stress in the keyway is really the difference between how much of that force is transmitted from the disc into your enemy, as how much, like when the disc stops, like if there was nothing, if the shaft was spinning, was freewheeling, if it didn't have a pulley attached to it and it was just, the spinning disc that just had spun itself up magically and then hit something and then stopped, the only stress in the keyway would be the stress that is needed to cause the shaft itself to decelerate, which would be relatively low. So in this sense, the keyway is the bridge between the deceleration, the angular deceleration of the disc, and the angular deceleration of everything behind the disc. That is to say, the shaft, the pulley, the motor, because the motor has a rotational inertia. Being able to calculate that rotational inertia, you could calculate that rotational inertia and then impart that as like extra mass on the shaft. Like you could give the shaft fake material properties to increase its moment of inertia, so that the moment of inertia would be representative of like all the moment of inertias of everything, downstream. And that would give you more accurate stresses in the keyway.
Yeah, that's also assuming that when the disc hits something, it's going to stop, which is not necessarily the goal of the weapon.
Yes.
So.
Yeah. Yes. But
it's the same thing where all of the force resulting from because it will slow down, resulting from the disc slowing down is going to go into the key.
Yes.
All right.
So if you wanted to simulate the stresses on the disc itself, one way to do that would be to open up the disc model as a single static part, simulation, new study, static, and then we'll just, put a fixed geometry in the center, and then apply a load to the tooth. And that would give you a sense of where the stresses in the entire disc are. So like you could more appropriately size this fillet. That would be one way to do it. Actually, with this, what I would do is I would not do fixed. I would do, so delete that. I would put a bearing constraint on there. Cannot define bearing connectors. Oh, sorry, fixtures, bearing fixture. A bearing fixture and a bearing connector are different things. So you apply force. Force 1 Newton is fine. Run the study. Okay. And it's going to say it failed because I don't have inertial relief. Turn on inertial relief, run the study. So you can see that when the disc hits something and it's coming to a stop, if it's not backdriving anything on the shaft, then you're going to have the majority of your stress is going to be here, which is pretty obvious, you know. And that's kind of your sanity check. And you can use this model, for example, in conjunction with the design study. I showed you how to do design studies in the last talk, where you could size the fillets and you could size the wall thickness of these spokes to you know, to minimize the stress in, you know, each of the fillets. So say if you had a stress in this fillet that was pretty high, you could do a design study to minimize the stress in that fillet, and so on and so forth. Fillets is pretty obvious. You know, you make a fillet bigger, you get less stress, or you could increase this wall thickness. But so as far as design feedback goes, you know, coupling FEA with experience, one thing about keyways is that the keys are not designed to be made out of hard metal. They're designed to be made out of soft metal. So the point of the key is that the key should shear, you know, into a semicircle before the rest of the system fails, and thus allow the disc to free spin around the shaft when the key fails. That may or may not actually happen. You know, just yeah.
And if it does, if we have a replacement for it, that could be a relatively easy fix. If the key fails in a way that it kind of breaks itself apart instead of breaking the shaft or the weapon itself.
Right. And so you should calculate the torque that the keyway will fail at. You look at the cross-sectional area of the key. So if the key is, let's see, evaluate, measure, from there to there is 625, so 15.8 millimeters. And then it is 4.76 millimeters wide. So you look at the shear area of this cross-section times the shear strength multiplied by the radius from the center of rotation, and that'll get you the torque that key will fail at.
All right. Yeah, that makes sense.
So so you want to make sure that the key is wide enough. This is why when you buy gears, you know, or sprockets, the sprocket is a thin disc, but it's got this gigantic thick boss at the hub, and that's because you need that width for the key to resist to be sufficiently big to resist torque.
Mm-hmm.
Now, in my own experience, I've bypassed this issue entirely.
Yeah, but
when
set screws.
No, I
No, really?
yeah, I don't use set screws. Set screws freaking suck. But no, I bypass the issue entirely. What I do is I have a solid shaft where there's no keyway at all. And the...
Oh, you mean in the FEA? Or in
no,
the
in the
design
actual design.
Okay.
Yeah.
With press fit?
No, so what I've used, what I used on my old robot is a robot called Tough Love. I don't have the CAD open for that because that one was done in Inventor. So, and my license expired yesterday. I'm trying to get it reinstated.
Oh boy.
Yeah. So for example, here's the weapon shaft assembly, and let's unhide that. So what I did on that robot was, instead of the key, I had a hole pattern where I actually so the shaft was a dead shaft, and the shaft was like bolted into the walls, the side rails of the robot.
Yeah.
And so the hub was free to spin on that shaft. I pressed a sleeve bearing, a bronze sleeve bearing onto the hub.
Mm-hmm.
And then I bolted the hub to the weapon disc.
Yeah, that's
using screws just sideways.
Yeah, that's pretty similar to how our other 15-pound robot is designed.
Yeah.
It's vertical. It's a vertical spinner though, so yeah. In my experience, this hasn't been the place that has failed, so figured it's worth trying different things.
Yeah.
But we're about out of time. Thanks, Rob, for putting this on. I think it's
sure.
a useful resource for all of us. Do you have anything you want to say in conclusion?
I've got some other design feedback for the robot if you guys want to stick around for that, but you know,
Sure.
It's mostly pretty minor.
Yeah, I'm gonna stop the recording and then we can go over that. Yeah.
Sure.